this. Okay, so problems like this would say determine if the integral converges or diverges. So you might have something, for instance, like let's do I'm just trying to find one that's like semi-nice. All right, what about the integral from 0 to infinity of 2 x e to the minus x squared dx? Okay, so this one is a problem, so you have to do the converging or diverging because of the infinity. So if one of your limits is either positive infinity or negative infinity, that is for sure one of the times that you're going to have to do these types of problems. And so we're going to turn this, into the limit as b approaches infinity of the integral from 0 to b of 2x e to the minus x squared dx. And then we have to actually figure out that integral, right? So I'll come over here on the side. A lot of times in these problems, I kind of do the integral on the side so I don't have to worry about the limits and all that stuff right away. So we're looking to do the integral of 2x e to the minus x squared dx. So how would I integrate that? I know you guys know how to do this. Or you at least have a guess, right? Like on Monday, or not Monday, Tuesday. Yeah, when you have to do something, you're going to have a guess. So parts, so I get why you might think parts, because it is two things multiplied together. But the thing you do want to look for is the power here is an x squared, and the power here is one less. So that's a good indication that it's a u substitution problem. So if we let u be equal to that power, minus x squared, du is going to be minus 2x dx. And I almost have all of that, right? I'm just missing the negative, so I need a negative inside. Can I zoom out a bit? Is it not showing my whole screen? There's nothing like this is the edge of my board. Like, can you not see that pink line I just put down? Okay, yeah. I'll wait for Julio to come back since he's the one who asked the question. So I will make sure he's back in here before I do the rest of this problem. Just because that's kind of crappy, right? It's like, oh, I can't see half of what you're writing, but, I'm the one that asked the question. So it is kind of the weird thing, right, about the online environment. It's not like in a classroom. It's also weird, too, how you can't. Okay, no problem. Okay, so we've got du is equal to minus 2x dx. And so now I end up with minus the integral of e to the u du. And the integral of e to the u is e to the u. So this is just minus e to the u. And so that's going to be minus e to the minus x squared. So I often just do the integral off on the side because in this problem, we only have to use that integral once, but in a lot of these problems, you have to use the integral more than once, and so doing it off on the side is helpful for that. And I just don't like to kind of get stuff cluttered because I have the limit and all that stuff, and I don't want to have to keep writing that a bunch of times. So now I'm going to come back and plug it back in. So we have the limit as b approaches infinity of the, so when we integrate, we have minus e to the minus x squared. And we're evaluating that from 0 to b. So in this case, it's going to be the limit as b approaches infinity of minus e to the minus b squared minus e to the minus 0 squared. And so here's where I'm going to rewrite it a little bit to help me figure out that limit in a minute. So this is really the limit as b approaches infinity. This is really minus 1 over e to the b squared. So that negative power on the b just drops it down. And then negative times negative is a positive. And then e to the 0 is just 1. So we end up with negative 1 over e to the b squared plus 1. And now if I think about plugging in infinity, we end up with minus 1 over e to the infinity squared plus 1. So this part here, right, e to the infinity squared, that's just infinity. So it's like some ginormous number. So I have negative 1 being divided by this ginormous number. And so it's going to 0. So this whole thing ends up being 0 plus 1 or 1. And because it came out to be an actual number, that's what says it converges. So converges. If it had ended up, if your answer was infinity or minus infinity, then it's going to diverge. If it's anything else, then it converges. So questions on that first one? No. Okay, so one of the ways that you could have integrals that are asking about converging or diverging is by this, where one of the limits is infinity or minus infinity. The other way that you could have converging or diverging integrals is, this is review. So everything today is review. The other way that you could have converging or diverging integrals is when you have an integral where you're trying to integrate over an interval where someplace in that interval the function would end up being undefined. So for example, b, if I took the integral from 0 to 4 of dx over the square root of 4 minus x. So here, that's not, actually, I'm going to change this just a tiny bit. Let's make it 0 to 5. So, it would have been fine if I did 0 to 4, but it's not going to illustrate the exact same point I want here. So this function here is undefined when x is 4, right? So the first thing I'm going to do is I'm going to split this integral apart into the integral from 0 to 4 of dx over the square root of 4 minus x, plus the integral from 4 to 5 of dx over the square root of 4 minus x. And then 4 is that problem part, right? So this is going to become the limit as b approaches infinity of the integral from 0 to b dx over the square root of 4 minus x, plus the limit as a approaches, oh, why did I put infinity? 4, I'm just used to the last problem where we were dealing with infinities, plus the limit as a approaches 4 of the integral from a to 5 of dx over square root of 4 minus x. Right, so there was a place where the integral was not, where the function inside the integral was not defined over the interval that we were integrating. So I split the integral at that point, so 4, and then we're going to basically replace the 4, which is that bad area, with the limit. And to be able to do the problem, we're going to have to do this integration. So I'm going to come off on the side and do this integration again, just because in this case, right, I'm going to have to integrate that same function more than once, and so I don't want to do it more than once. So we're going to come over here on the side. We're looking at the integral from, and let me just restart it just in case. I don't want to lose everything here. So we're looking at the integral from, we're not going to put any limits because I just want to know what the integral part is. So the integral of dx over the square root of 4 minus x. So how are we going to integrate that? What should we do to integrate dx over the square root of 4 minus x? Yeah, so this is just another u substitution integral. So we're going to let u be the stuff inside that square root. So u is 4 minus x. So du is going to be minus dx. So again, the only thing I'm missing is that negative. So this is going to be minus the integral of du over the square root of u, or minus the integral of u to the negative 1/2 du. And then I have to actually integrate this, right? So if I add 1, we're going to have minus u to the 1/2 over 1/2. Or this is going to be negative 2, and then our u is 4 minus x to the 1/2 power. And remember, 1/2 is just square root. So we've got minus 2 square root of 4 minus x. Questions so far? No. Okay, so we're going to plug in here. So I'm going to work on the first limit first. Won't 4 to 5 be completely undefined? Oh, yeah. Brian's letting me know that I messed up by changing the problem at the beginning. Yeah. It was just a bad problem. See, this is what happens when I just randomly pick a problem and then try to change it. See, I told you guys, oh, I shouldn't try to just change a problem. And then I did. All right. Let me pick a different problem. I wanted one that wasn't ridiculously messy. All right. So we'll just put Dr. Gorman, bad problem. Okay. I think I have one. Okay, so let's do the integral from 0 to 2 of t over t squared minus 1 dt. Okay, so problem here is that when you plug in 1, oh, it's lagging. Oh, yeah, I see that. All right, let me disconnect and then start recording again. Okay, so quick recap for the record. I started with this problem. 1 makes this undefined, right? So That's why I split it into two integrals from 0 to 1 and then 1 to 2. And then I'm replacing the bad place, which is 1, with b approaches 1 for the first integral and a approaches 1 for the second integral. And now we're just going to integrate it. So we're looking at the integral of t over t squared minus 1 dt. And so in this case, it's a u substitution. So we're going to let u be t squared minus 1. du is going to be 2t dt. So I need a 2, which means I have to balance with a 1/2. So we're going to end up getting 1/2 the integral of du over u. And what's the integral of du over u? Yep, natural log. So 1/2 natural log absolute value of u. 1/2 natural log absolute value of t squared minus 1. So I'm going to come back over here. I'm going to work on the first limit. So let's just see what happens with the first limit, and then we'll figure out if we have to do the second limit. So the first limit here, we're looking at the limit as b approaches 1 of, get rid of that, 1/2 the natural log absolute value of t squared minus 1 evaluated from 0 to b. So it's going to be the limit as b approaches 1 of 1/2 the natural log absolute value of b squared minus 1 minus 1/2 the natural log absolute value of 0 squared minus 1. So if I clean this up a little bit, we have the limit b approaches 1, 1/2 natural log absolute value of b squared minus 1 minus 1/2 the natural log of 1, and the natural log of 1 is 0. So this whole second piece goes to 0, which is nice. And now to look at the first piece. And so if I try to plug in 1, right, this ends up being 1/2 the natural log of the absolute value of 1 squared minus 1. So we're trying to find 1/2 the natural log of 0. Now, you have to remember what the natural log graph looks like, right? It looks like this. So what happens to the natural log graph as you're approaching 0?
Undefined.
Yeah, it's undefined. Yep. And so the graph itself, though, as you're approaching 0, is going where?
To the left.
Okay, it's going to the left and it's going down forever, right? So when the graph goes down forever, it approaches what value?
Negative infinity.
Okay, negative infinity. So this first part here ends up being negative infinity. And that right away tells us that this graph diverges. That this integral diverges. That there's nothing we can do. The integral is not going to settle down and just become some number. Doesn't matter what the other side does. This first side diverges, and that's all that matters. So as soon as you get one of the pieces that diverges, the whole entire thing diverges. Questions? Like one where two pieces converge, you're saying? Okay, so getting two pieces to converge is actually like a little hard. That's why I did one of them last class, because I'm not going to be able to just pull a problem off the top of my head and get both of them to converge. And so if you want to see one where they both converge, you want to go back and watch. I'm going to put up the link. I ran into an issue with YouTube, so I had all these videos and they just didn't upload until a tiny, like, I had to set them to go overnight, and I just haven't had a time to get the links for them yet. But I will put them up after class. So the very first problem I did last class was one where it's two pieces, you have to split apart, and both pieces converge. Just because, like, it takes a little bit of effort to get that to happen. So the chances that I randomly pull a problem and get one where both pieces converge is going to be real slim. Does that make sense? No problem. Yeah, I'll go back to the first problem 1 second. So, no, I'm not saying that one that converges would be one where they both converge would necessarily be on the test. It could be one where one piece diverges. It could be either one. I haven't written the test yet, so I don't know what I'm putting on the test yet. It's just, I don't want to just pick a problem off the top of my head or just look at the book and go, yeah, I think that's an okay problem, because the chances are it's not going to be one where both pieces converge. It just takes a tiny bit of thought. It's not that it's a hard problem. It's not that it makes the problem harder to do. It's just you have to be careful when you're crafting the problem. So, yeah, the first problem, Robert asked me to go back to the first problem. So the first problem converges. The reason it converges is because you get a number. So if you get an actual answer, 0, 1, 17, minus 3.76, it's going to converge. If you don't get a number, if you get some type of infinity, then it's going to diverge. Let's see. Could I do an improper integral where I have to use L'Hopital's rule? I messed that up on the homework questions 5 and 6. Yeah, do you want me to just do one of those homework questions? Okay. Anyone in particular? Would you rather 5, 6? Doesn't matter. Both. You pick. I'm here to do what's best for you guys. Okay, fine. Let me go find problem 5. Oops. Okay. Keep recording. Let's see. Okay, so problem 5 gives us the integral from minus infinity to 0 of theta e to the theta d theta. Okay, 3a and 3c. Okay, so I'm going to do 5, and then, Sandra, are you saying 3a and 3c on the review sheet? I just want to make sure I know what I need to do next. Okay, I'll do those next. Okay, so again, I look at this problem, 5, so this is 5 from the 9.7 homework. And the first thing I see is that one of the limits is going to infinity. So I'm going to have to change this into a limit problem. So it's going to be the limit as a approaches negative infinity of the integral from a to 0 of theta e to the theta d theta. And again, I'm going to come off here on the side and do that integral. So we're looking for the integral of theta e to the theta d theta. So what am I going to have to use to integrate theta e to the theta d theta? Yeah, so I'm going to have to use parts. So if we let u be equal to theta and dv be equal to e to the theta d theta, Then du is just d theta. And v is going to be the integral of e to the theta d theta, which is just e to the theta. And so we end up with uv, so theta e to the theta, minus the integral of v e to the theta du, which is just d theta. And then the integral of e to the theta is just e to the theta, so we have theta e to the theta minus e to the theta. So any questions about how I did the integral? Let's start there first. No. Okay, so this is going to be the limit as a approaches minus infinity of our answer, theta e to the theta minus e to the theta, evaluated from a to 0. So we're going to plug in the upper limit. So limit a approaches minus infinity of 0 e to the 0 minus e to the 0 minus theta e to the theta minus e to the theta. I want to put a's, not thetas. Let's just rewrite that. A e to the a minus e to the a. So if I kind of work some of this stuff out here a little bit, I have the limit as a approaches minus infinity of 0 minus 1 minus a e to the a plus e to the a. And so sometimes in these problems it's helpful if you think about when I'm taking this limit, I'm really taking the limit of each of those pieces. And we don't need that 0, right? So this is really the limit as a approaches infinity of -1 minus the limit as a approaches infinity of a e to the a. Oops, and it's negative infinity, right? Negative infinity, plus the limit as a approaches negative infinity of e to the a. Okay, so that first limit, right, the first piece, it doesn't have any a's in it, right? So as a gets really, really big, it doesn't matter. That first limit is just still staying as -1. So this first one here is -1. This second one, I have minus negative infinity times e to the negative infinity. And this last one, I end up with e to the negative infinity. So, thing to remember is that e to the negative infinity, this is just saying 1 over e to the infinity. So 1 over e to the infinity would get really, really, really big. 1 divided by some ginormously big number is going to go to 0. So this piece here is going to 0. So we really have -1 plus, well, I'm going to leave it as a minus. This part here is a problem. And the reason it's a problem is because it's a minus infinity, but then we just said e to the minus infinity goes to 0. So I have this like weird minus infinity times 0 going on. And then this last piece is 0. So this middle limit is an issue. And it's just, we're going to have to figure out what to do with it. So rather than having to keep writing the -1 part and all that, I'm going to come over here on the side again, and I'm going to do the limit as a approaches minus infinity of a e to the a. And so we said that this, I just worked this out for us. So we said this is minus infinity times 0. So we're going to work out this limit. So questions on anything I've done so far before we actually work out the limit? No. Okay. So yeah, we're going to use L'Hopital's rule for this part, but we can't use L'Hopital's rule the way it's written, right? So to be able to use L'Hopital's rule, you have to have 0 over 0 or infinity over infinity, and I don't have that. All I have right this second is minus infinity times 0. So what I want to do is I want to somehow, so if you end up with infinity, times 0, you want to somehow make it into a fraction. And so Sandra said, well, we could rewrite it as a over e to the minus a. And that's exactly what we want to do. So this is going to become the limit as a approaches minus infinity of a over e to the minus a. So you can take any term you want and push it down to the bottom of a fraction. But when you do that, you have to make the exponent negative. And so now, if I plug in, I have a minus infinity on top, and I have e to the infinity on the bottom. So now I have infinity over infinity, which means now I can do L'Hopital's rule. So L'Hopital's rule says, okay, well, take the derivative of the top, so just 1, divide by the derivative of the bottom, which is going to be e to the minus a, times negative 1. And so now I can plug in here. And so if I plug in here, we have the limit as a approaches negative infinity. So we're going to end up with 1 over e to the negative infinity times negative 1. So we end up with 1 over e to the infinity times negative 1. And so again, e to the infinity is some ginormously huge, big number. 1 divided by some giant number is 0. So this middle limit here actually also turns out to be 0. Which means my final answer is negative 1. And since it was one of these problems, does it converge or diverge? I got an actual concrete answer. It means it converges. Does that help for 5?
I had a question.
Sure.
So, you're treating a as a constant when you take the derivative of it?
No, I'm treating a as a variable. So it's just like when you take the derivative of x, you get 1, so the derivative of a would be 1. So a is just like an x, except instead of an x, it's a different letter.
Got it. Thank you.
No problem. Other questions on this one? No. Okay. So then Sandra asked for 3A and 3B from the review sheet. So let me pull the review sheet back up here. Okay, the L'Hopital rule ones. Okay. Okay, so 3A asks for the limit as x approaches 1 of x squared plus 3x minus 4 over x minus 1. 3b, I'll just write it while I'm writing stuff, is the limit as x approaches pi of the tangent of x over x. Okay. So if we... yeah, go ahead.
With 3a, my question is really like, you did L'Hopital's rule to solve it. Why wouldn't we just do the algebra of doing the factoring on the numerator, which will cancel it out with the denominator beforehand?
You could totally do that.
Okay, so that would be okay, because your instructions didn't say specifically to use L'Hopital's
Nope.
rule.
Yep.
So I just did the factoring and canceling, and it made it a lot quicker.
Yep, that's totally fine. You can totally do that. And then was it 3B or was it 3C you wanted?
No, it was actually C.
Oh, okay. That's fine.
That one was more of a question towards the end. I feel like the last time you did L'Hopital's rule, because you have to do it multiple times, something went different with my derivative.
Okay.
The denominator, however, I did end up with the same answer.
Okay. So we can go through that one. So now that I have them all written down. So while they're up there, let's go through them one by one in case anyone else wants any of the other ones. Does anybody want me to do 3A? No. Okay. Sure. Okay. So I will get to it, Sandra, I promise. So let me move 3C over here. Okay. So 3A you could do one of two ways. So you could, the first thing you could do, so no matter which way you're doing it, the first thing you should always do anytime you do a limit problem is plug in, right? So if I plug in, you would get 1 squared minus 3 times 1 minus 4 divided by 1 minus 1. Did I copy this right? Oh, I wrote right there. I wrote it wrong. I'm like, wait, something's not right here. Okay. So 1 squared plus 3 times 1 minus 4. So in this case, you get 0 over 0, right? And so now you have a choice. You could either do the problem the way that you would have done it in Calc 1. So this is a Calc 1 problem, right? So in Calc 1, we did problems like this. When we got 0 over 0, one of the first things we would try to do is factor. So you can actually factor x squared plus 3x minus 4. It would factor into x plus 4, x minus 1, all over x minus 1. Cancel the x minus 1s. Plug in, you end up with 1 plus 4 or 5 as your final answer. So that's totally fine. Nothing wrong with that. You can definitely do the problem that way. You could have, so we'll say, or, when you saw 0 over 0, you could have been like, hey, I know this cool thing called L'Hopital's rule, so I'm going to use L'Hopital's rule. So limit as x approaches 1. L'Hopital's rule says take the derivative of the top, so it would be 2x plus 3, over take the derivative of the bottom, which is 1. I plug in, I have 2 times 1 plus 3, all over 1, which is also 5. So no matter which way you do it, you end up with 5, right? And I don't care. If you had factored it and done it, that's totally fine. If you did L'Hopital's rule, totally fine, either way. So that's 3A. Questions on 3A? No. 3B, right? Because people sometimes, as soon as I teach something, they think, oh, I have to use this all the time, right? So, oh, I have to use L'Hopital's rule all the time. 3B, the limit as x approaches pi of tangent x over x. If you plug in, you get the tangent of pi over pi. And what's the tangent of pi? Yeah, 0. So you end up with just 0 over pi. And 0 divided by pi is what? Yeah, 0. So this is not a L'Hopital's problem at all. It's just a plug and chug problem. So in this case, the limit is just 0. Questions on 3A or 3B before I go to another page to do 3C? No. Okay. So let me paste 3C here. Okay, so 3C, again, the very first thing you should always do is try to plug in. So if I try to plug in, we end up with sine squared of 0 over tangent of 0 squared. And so the sine of 0 is what? Yeah, 0. And then on the bottom, I have the tangent of 0 squared. So it's going to be the tangent of 0, tangent of 0 is 0. So I end up with 0 over 0. And so here's one where you can't factor. So this is where you're going to have to use L'Hopital's rule. So L'Hopital's rule says, okay, take the derivative of the top. So remember, sine squared x means, this really means sine x all raised to the second power. So the derivative is going to be 2 sine x times the derivative of the stuff inside. The derivative of the stuff inside is cosine x. And then we have to take the derivative of the bottom. So the derivative of tangent is secant squared. The stuff stays the same. So secant squared of x squared times the derivative of the stuff inside, which is going to be 2x. So just to make my life a little nicer, I'm going to cancel the 2's. And I'm going to rewrite this. So this is, we're looking at the limit as x approaches 0 of sine x cosine x divided by x secant squared of x squared. And I need to plug in, right? So if I plug in, we've got sine of 0 times the cosine of 0 divided by 0 times the secant squared of 0 squared. And so this ends up just being 0 over 0 again. And so that can happen, right? Sometimes you have to do L'Hopital's rule more than once. So here's one of the cases where you have to do it more than once. So we are going to use L'Hopital's rule again. This is why I took that time to kind of clean it up and make it look a little nicer. So we need to do L'Hopital's rule. L'Hopital's rule says take the derivative of the top. So what am I going to have to use to take the derivative of the top? Yep, the product rule. So first times the derivative of the second. Derivative of cosine is minus sine x. Plus the second, cosine x, times the derivative of the first, which is cosine x. So first times derivative of second, plus second times derivative of first. And then on the bottom, we're going to have to use the product rule again. And within the product rule, we have a chain rule. So it's all sorts of fun in the bottom. So on the bottom, if I did first times the derivative of the second. So remember, secant squared of x squared, this is really saying that I have secant of x squared all squared. So it's going to be 2 secant of x squared times the derivative of the secant part. So the derivative of secant is secant stuff, tangent stuff. So it's going to be secant of x squared tangent of x squared times the derivative of the stuff, which in our case is 2x. And I need a much longer line here. So that's all just first derivative of the second, plus the second, which was the secant squared of x squared times the derivative first, so times 1. Guess I made my line a little too long. Okay, so questions about anything I did there, how I got any of those derivatives. Yeah, it's a lot. All right, no questions. All right, so now I need to plug in. So, whoops. We're going to have the sine of 0 times minus the sine of 0 plus the cosine of 0 times the cosine of 0, all divided by 0 times 2 secant of 0 squared times the secant of 0 squared times the tangent of 0 squared times 2 times 0 plus the second one is just the secant squared of 0 squared. So this whole first thing on the bottom, this is all just going to 0, right? I have 0 times a big thing, and it's got a bunch of zeros being multiplied in it anyway. So it's just all 0. The sine of 0 is 0, which means this whole piece here is 0. So we have the cosine of 0. So what's the cosine of 0? 1, right? So we're just left on the top with 1 times 1 divided by on the bottom. So if the cosine of 0 is 1, that means the secant of 0 is also 1. So divided by 1 squared. And our whole entire thing is 1 over 1. Or finally, we got to the answer 1. Did that help, Sandra? You clean up the denominator to secant squared of x squared. Okay. Plus 4, yeah, x squared. Yup. Secant squared x squared tangent x squared. Yep, yeah, that's the same thing. No problem. Other questions? Either on this problem or other problems. 1W. Okay, let me find 1W. Okay. Up here. So 1W asks for the integral from 1 to 2 of 1 over x ln x dx. Okay, so a couple things to note. This is an improper integral, right? Because if you plug 1 in, it makes the denominator 0. On the test, right, the improper integral problems will be separate. So I won't, unlike this review sheet where you got lucky and there were a couple improper integrals just mattered in with all the other ones, I will not do that on the test. So on the test, it will be integrals that I expect you to integrate. And then there will be a section that says, determine if the following intervals converge or diverge. Okay, so this would be a problem that would be in that section. So it would be clear that it's somehow an improper integral. So I'm not trying to like trip you up and get you to like, oh, I integrated it, and then, oh crap, I didn't realize it was an improper integral. So just to kind of make you aware of that to begin with. So the problem here is that 1. So this is going to become the limit as b approaches 1 of the or b is fine. I guess to keep with the way I've been doing it, I should make it an a because it's a bottom. A approaches 1 from a to 2 of 1 over x ln x dx. Okay. So let's come over here on the side and integrate our integral. So we're looking at the integral of 1 over x ln x dx. So how could we integrate 1 over x ln x?
So just before we go that far,
sure.
I actually, the big question that I have is, when we're separating them, what about 0? Because the natural log of 0 is undefined.
Sure, so the natural log of 0 is undefined. However, 0 is not in your interval here. So you're only worried about the stuff that's in your interval. So your interval is only going from 1 to 2.
I think I did it from -1, that's why.
Yeah, I don't think, unless I wrote the problem wrong. No, it is. It's a positive one.
Okay, just making sure.
Yeah, if it was a -1, then you're right. You would have to worry about 0 as well, and that would be like a much uglier problem.
Yeah.
Yeah. Other questions about what I did so far before we actually do the integration part? No. Okay. So how are we going to integrate this integral? Yeah, so we're going to do a u sub. So let u be equal to natural log of x. So du is going to be 1 over x dx. And I happen to have the 1 over x dx, right? Here's my 1 over x and my dx. So all that stuff's going to become my du. So this is going to be the integral of 1 over u du. And what's the integral of 1 over u? Yep. Oh, I'm reacting to your last comment. What's the integral of 1 over u? Yeah, the natural log of the absolute value of u. So this is going to be the natural log of the absolute value of the natural log of x. Okay, so we have the limit as a approaches 1 of the natural log, absolute value, natural log of x, evaluated from a to 2. And so what we're going to do is we're going to plug 2 in. So plug in the upper limit. So we've got limit as a approaches 1 of the natural log of the natural log of 2 minus the natural log of the natural log of a. Okay, so this becomes the natural log of the natural log of 2 minus, when I plug in a, we end up with the natural log of the natural log of 1. Now, the natural log of 1 is 0. So now we're talking about the natural log of the natural log of 2 minus the natural log of 0. And what did we say before happens to the natural log as you approach 0? Yeah, it goes to minus infinity. So I've got the natural log of 2, minus infinity. So this whole thing just ends up being infinity, and it would diverge. Questions? Okay, so why does the natural log of 0 go to infinity? So you have to remember the natural log graph. So remember the natural log graph looks like this. Goes through 1. And so as you approach 0, so here's 0, right? As I'm approaching 0 along the curve, I'm going down, 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 down. So it's going down to negative infinity. Does that help? No problem. Right. The other weird thing to remember about the natural log graph, right, is even though it grows really, 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 really slow, it does continue to grow upward forever. So the so the limit as x approaches 0 of the natural log of x is minus infinity. There's a little bit of wiggle room because it's technically only a one-sided limit, but for all purposes, we think of it as minus infinity. The limit as x approaches infinity of the natural log of x is just infinity because it keeps growing forever and ever and ever. It keeps going up. So the natural log graph is not defined on any negative numbers. So you're never taking the natural log of negative infinity. That like doesn't even like it wouldn't even be something that would come up in a problem because you can't take the natural log of a negative number. Other questions? One T. Sure. Is everyone okay if I move on to the next page? Used to get these problems. So like the natural log of a negative number, the natural log of 1 is 0. So, the natural log of 1 is 0, but that's the only place that the natural log is equal to 0. Well, it depends, right? So here's a good point that sometimes, like depending what it was that was telling you it was 0, right? So this is where all those apps and stuff like that solve problems. They give you the right answer most of the time, but they begin to break down once you start getting stuff with infinities and stuff like this, because it doesn't really know how to handle it, because it's when computers and stuff like that do math with infinities or places where functions are undefined, it's actually using an algorithm in the background that's not actually infinite. And so it's basically essentially doing an approximation, but the approximation is usually so good that it doesn't matter that it's approximating. But as soon as things go a little funky, those approximations go haywire. And so it might still spit you out an answer, but that answer is no longer right anymore. So that's kind of why professors can tell if you're using an app or not. So like in my Math 95E class, it's very simple because there are problems where an app just doesn't know what to do with some of the stuff. And then you just get this random stuff and like people magically have this answer and you're like, no, I know you took that from someplace. So it depends when you say the computer said it was 0. Like, I don't know what computer, like, if it was an app or if it was a homework program or what. So anyway. Okay. 1T. So I think I accidentally, whoops, wait a minute. I think my math lab might have, so then it was probably a natural log of 1. You mean on my solution, Sandra? I have the same thing on my solutions. I just want to make sure I answer your question before we go on. Oh, you mean in 1T, not in 1W. Oh, no, that's okay. I was just like, wait a minute, 1W. Okay, wait, let me look at 1T, and then 1T. Oh, you're right. I did accidentally just change my bounds in 1T. Yeah, so I can do the correct problem. That I should make a note to fix that too. Okay, but here, we'll do it here so that everybody has the right answer. So the original problem should be 0 to infinity of 1 over x plus 1 cubed dx. Right? And, so we're going to, again, this is an infinite one, right? So we're going to change this to be the limit as b approaches infinity of the integral from 0 to b of 1 over x plus 1 cubed dx. And again, if I come over here on the side and I integrate the integral of 1 over x plus 1 cubed dx. And you might have, you'll see on the solution when I integrated it, I just wrote down what it was, because this is really just the integral of x plus 1 to the minus 3 dx. And so when I look at this, I personally don't need to do a u substitution anymore, because I've integrated things like this so many times that I can look at this and say, oh, I just have x to the first power. So when I do a u substitution, just instead of an x, like, I'm going to integrate this as if it was like thinking that this is a u in here, because nothing's going to change, right? So when I let u be equal to x plus 1, du is just going to be equal to dx. But I'll do the u substitution out. There is no shame or anything like that in actually doing the u substitution out. It's just you get to a point where you've like integrated things like this so many times that you're just like, yeah, I know what the answer to this is. But if you did the u substitution, you'd have u equals x plus 1. So du is going to be dx. So this is going to be the integral of u to the negative 3 du. I should have made that. So this is going to be u to the negative 2 over negative 2, or x plus 1 to the negative 2 over negative 2. And so this is where I personally just jump from here right to here. Like, I don't need to do the u substitution. But if you need to do the u substitution, get it right, by all means, do the u substitution. So we end up with the limit as b approaches infinity of x plus 1 to the negative 2 all over negative 2 evaluated from 0 to b. So here's where I made my mistake. I changed it to a 1. And so we're going to end up with the limit as b approaches infinity of b plus 1 to the negative 2 over negative 2 minus 0 plus 1 to the negative 2 over negative 2. Or the limit as b approaches infinity. So I'm going to rewrite this. This is 1 over minus 2 times b plus 1 squared. The second one, the minus and the minus are going to make it a plus, and then we just have 1/2, because 1 to any power is 1. And so if I plug in infinity, I have 1 over minus 2 times infinity plus 1 squared plus 1/2. This whole part here goes to 0. And so your final answer should be 1/2 rather than what I have, which is 1/8. So yes, I messed that up. Questions on it though? No problem. Thank you for doing it and letting me know it was wrong. So now everybody else knows that 1t, the answer to 1t is wrong too. Other questions? Sure. Okay, 1, is that L or I? L, okay. Let me see. Okay. So let me write it down here. So 1 L is the integral of x cubed over x minus 1 to the 4th dx. Okay, so we'll take care of the integral here in a second. So we're looking at this x cubed over x minus 1 to the 4th, right? And you can split up x minus 1 to the 4th as a over x minus 1 plus b over x minus 1 squared plus c over x minus 1 cubed plus d over x minus 1 to the 4th. And so even though it's crazy you have to find the a, b, c, and d, integrating each of those fractions is actually not that bad. So if I clear the denominator, so I multiply everything by x minus 1 to the 4th, we end up with x cubed is equal to a times x minus 1 cubed plus b times x minus 1 squared plus c times x minus 1 plus d. So are we questions on any of that stuff to begin with? Let's start there. No? Okay, so if you are someone who likes to like cube that stuff out, if you, when we've been doing these problems, have liked to multiply out this right hand side and then match up the coefficients, this is going to get super ugly for you super fast. So instead, I'm going to pick values to plug in. And it's not that it's going to make it like real quick to find all the values, A, B, C, and D, but it'll at least, I think, it's a little cleaner. So there is one really nice value of x to plug in here. So anybody want to guess what the nice value of x to plug in? Yeah, so 1 is the really nice value. So if you plug in x equals 1, we'd get 1 cubed equals a times 1 minus 1 cubed plus b times 1 minus 1 squared plus c times 1 minus 1 plus d. And so this is nice because all of these parts go to 0, and I can just find out, excuse me, that d ends up being just 1, right? So at least I have one of the values pretty quickly. So I'm going to pick other values. So what's another value for x that you might use? Yeah, 0. You can use any values you want, right? Like if you want to use 100, you can, but your numbers are going to get terribly big. So x equals 0 is a good one. So if we pick x equals 0, we get 0 cubed equals a times 0 minus 1 cubed plus b times 0 minus 1 squared plus c times 0 minus 1 plus d. So we would have 0 is equal to, this is a times negative 1 cubed plus b times negative 1 squared plus c times negative 1 plus d. But remember, I already know that d is 1. So I'm just going to put that in right this second. So I end up with 0 is equal to minus a plus b minus c plus 1. Or I can move that 1 to the other side. So negative 1 is equal to minus a plus b minus c. So I can't figure out a, b, or c yet, but I at least have one equation that gives me a relationship between a, b, and c. And so now I'm just going to pick another value. So what's another value you could plug in that's semi-nice? Okay, -1. So we get -1 cubed equals a times -1 minus 1 cubed plus b times -1 minus 1 squared plus c times -1 minus 1. And again, d we know is 1. So I get -1 equals, this is -2. -2 cubed would be -8. So we get a -8a. -1 minus 1 is -2. -2 squared is 4. So 8a plus 4b minus 2c plus 1. And again, if I move the 1 to the other side, I have -2 equals minus 8a plus 4b minus 2c. So I have a second equation that has an a, b, and c in it. And I'm going to move this up here a little bit. What's another nice value to pick? Yeah, 2. So if I look at x equals 2, I'm going to have 2 cubed equals a times 2 minus 1 cubed plus b times 2 minus 1 squared plus c times 2 minus 1 plus, again, d is 1. So we're going to have 8 is equal to, 2 minus 1 is 1. 1 cubed is 1, so a. 2 minus 1 is 1, so a plus b. 2 minus 1 is 1, so plus c plus 1. And if I move the 1 over, I have 7 equals a plus b plus c. So that is my third equation, right? So I have 3 equations here. I have, I'm going to kind of come up on the other side here. So I have -1 equals minus a plus b minus c. I have -2 equals minus 8a plus 4b minus 2c. And I have 7 equals a plus b plus c. Questions about any of that so far? Okay, so now it's a matter of kind of your preference. I think the answers on the review, I took one of the equations and solved it for one of the variables and then plugged it into the other 2 and then had 2 equations. I could have been a little smarter. If you look at this first equation here and this third equation here, if I were to add those 2 equations together, right? So if I add them together, -1 plus 7 would give me 6. The a's would drop out. I'd have 2 b's and my c's would drop out. So b is going to be 3. So b, when I divide both sides, b would end up being 3. So that's like a little bit quicker way to do it. So if I plug b into those 3 equations, I now have -1 equals minus a plus 3 minus c. The second equation, I have -2 equals minus 8a plus 4 times 3 minus 2c. And I could use those 2 equations to find c, right? That first equation is going to tell me that if I move the 3 over, it's going to tell me that -4 is equal to minus a minus c. And the second equation, this is going to be 12. So if I subtract the 12 over, I would have -14 equals minus 8a minus 2c. And you have a couple options. We could just multiply the top equation. Yeah, that's exactly what I was going to do. We can multiply the top equation by -2. And if I do that, I have 8 equals 2a plus 2c, and my bottom equation is minus 14 equals minus 8 minus 2c. So the c's would go away. I'm going to have minus 6a equals minus 6. So divide both sides by minus 6. And a is going to be equal to 1. And then I could just plug into one of the equations, right? So if I plug into the first one, I know minus 4 is equal to minus a minus c. So minus 4 is equal to minus 1 minus c. So minus 3 is equal to minus c. So c is going to be 3. So I hopefully got the same thing I got on my paper. So A is 1, yeah, B is 3, C is 3, and D is 1. Okay. So, before we haven't even gotten to a point where we can integrate, right? But we're at least really close to a point where we can integrate here. Does anybody have any questions with anything I've done? Yeah, no, there won't be anything this crazy on the test. So remember, right? My goal is not to trip you up on the test, right? I think things like this are fine in a review sheet because it makes you work a little bit. But my goal on the test is to make stuff pretty straightforward. This is pretty ugly, right? So, questions. We're not done yet. I am going to finish the problem. Okay, so let me kind of move stuff up here. Yeah, different people like this. It kind of just depends. So we're now left with our integral is now going to be the integral of a. So it was 1 over, I think it was x minus 1. Yeah, okay. 1 over x minus 1 plus b is 3. So 3 over x minus 1 squared plus c is 3 over x minus 1 cubed plus d is 1 over x minus 1 to the 4th power dx. And again, you could do use substitution for each of these pieces, but I'm going to look at them and go, okay, I know that first piece, since it's just x to the 1st power, this is going to end up being the natural log of the absolute value of x minus 1. If I needed to do a use substitution, let u equal x minus 1, figure out what's going on, it's totally fine. This second one, I have x minus 1 to the negative 2 power. So we're going to have 3 x minus 1 to the negative 1 divided by negative 1. The next one is going to be 3. I have x minus 1 to the negative 3 power, so it's going to be x minus 1 to the negative 2 over negative 2. And then that last one is 1 times x minus 1 to the negative 3 over negative 3 plus a constant. And you could leave it. You could leave the problem like that, or you could rewrite it to make it a little bit nicer if you wanted to, right? If you really wanted to, you say, all right, it's natural log absolute value of x minus 1 minus 3 over x minus 1 minus 3 halves times 1 over x minus 1 squared minus 1/3 times 1 over x minus 1 cubed plus c. But you could definitely just leave it here. I'm okay with that. Does that help for that problem? Is there a pattern with how many variables and how many times you need to plug in for x? Yeah, exactly. So if you're trying to find, like we had 4 on, I think, let me answer your question, and I think I know what you're asking. At the beginning, we had 4 unknowns, right? We had A, B, C, and D. So since we had 4 unknowns, you're going to need 4 different values of x to plug it in. If you happen to have 5 unknowns, you would need 5 different values of x. If you had 2 unknowns, you're going to need 2 different values of x. Does that answer your question? Yeah, so however many variables you have, that's how many different values of x you're going to have to pick to plug in.
Yeah, I think the problem that I had with this was whenever I got to the -1 equals -a plus b minus c, and then the next one that I did, I tried to do elimination from there. I think it screwed me up, and then I had to like look at what you did and follow along a little bit.
Yeah.
So for these, I just want to always solve that amount of times and then start looking at it, right?
Yeah. Yep. Yeah. You want to find all the equations first.
Okay, so I was on the right track just in...
Yep. Yeah. You just didn't quite finish it.
Alright, thank you.
No problem. So Robert, the way that I found, so once I found that B was 3, what I did was I went and I just looked at these first 2 equations and I plugged 3 in for B. And that's how I came to these 2 equations. So if you plug 3 in for B, that's how I get to -4 is equal to -a minus c, and -14 is equal to -a minus 2c. And then you have multiple ways you can find it from there. Some people like substitution, so you could have solved one of these equations for one of the variables and then substitute it into the other one. But I just used elimination, so I decided, well, let me get rid of the c's. And so I multiplied the first equation by -2, which basically when I multiply it by -2, I come down here, that's what gives me the 8 equals 2a plus 2c. And then here, excuse me, I have the -14 equals -8a minus 2c. So now when I add these 2 equations together, my c goes away, and that allows me to find a. Does that help with what I did? No problem. Yeah, it's a lot. It's a long problem. Like, I wouldn't ask you something like this on the test. While you guys are looking to see if you have any other questions before I lose anyone. So, okay, I went through all the homework except 9.7. So, because 9.7 is not due till Monday. I have videos for all the ones you guys asked about, for the most part. So, there were a couple people on a couple of the different sections that just wrote, I want to see every single problem, right? So I didn't do every single problem in all the sections. The first section, the stuff from section 8.2, I did almost every single problem. But I didn't do, so there's 2 I still didn't do. So, no one asked me about problem number 1 specifically, so I didn't do problem number 1. The other one is that one that I made a typo on, and I will write out the answer for that one that I made a typo on, but I'm not going to do a video. It's just terribly ugly. Like, the algebra is terribly ugly. Like, it's a terrible problem because I typed it wrong, okay? So I know some people really want to see it. I will write it out, but it's, like, on the back burner. So it didn't get done yet. So I did upload all those videos last night, but I didn't send you an email and I didn't put the links up on Canvas yet, just because, like, by the time I finished, it was like 12:30 last night. And so I wasn't staying up the, like, 2 hours everything was going to take to upload to YouTube because I had a bunch of stuff I had done last night. So I will put them up. I will send out an email this afternoon. So I'm finally all caught up. You'll see some of your homework grades got caught up. I will catch up the rest of the homework grades. And so then I should be back on top of things. And so the videos should come out a lot faster than they did here, for future sections. That being said, I do want to say, like, I am more than happy to help anyone who's like, I don't understand any single one of these problems and I need stuff explained to me. But if that's you, when you're filling out that homework, like, self-assessment, and when it's like, are there any other problems you want to see worked out? If you are going to write, like, I want to see every single one, like, I'm not going to do every single one in a video. Like, there's just not enough hours in the day. that being said, if like you are one of the people who's writing that, please either come see me in my office hours or reach out and send me an email and be like, hey, I'm thoroughly confused on this stuff. I can't make it to your office hours, but I need to find a time to meet with you, something like that, right? Because if it's that you need to see every single one worked out, like explained to you out loud, as opposed to just looking at my solutions, there's nothing wrong with that. It's just that I want to meet with you so that I can figure out what is it you don't understand. Because at that point, there's probably some fundamental thing you're missing. And even if I make a video, that may not help you. So I want to make sure that I'm there to help you. So if you're in that situation, I don't want you to think like, oh, I just ignored, Dr. Gorman just ignored the fact that I wanted everyone worked out. I'm not ignoring it. I'm telling you that in that case, you and I need to like sit down so that I can help you out, like in a more individualized way. So I just want to say that before I send out the links. So they will be coming sometime today. Hopefully pretty quickly after class. But if not, before I go to bed tonight, I will send out the email that has all those links and I will post all that stuff to Canvas. So I wanted to put that out there before anybody else, before we were done for the day or before anybody asked me any other questions. So other questions? No problem. Nothing else you guys want me to go over? No. Okay, well, if you have another question you want to stick around, feel free for it. If not, then good luck studying. If you have any questions while you're studying over the weekend and stuff like that, feel free to send me an email. Yes, so that's a good point. And I'm going to put this in my email. I'm going to put up the helpful trig information up on Canvas, and I will put it up actually, like I'll do that tonight too. I'll put that up tonight. That way, if you want to be able to print it off to use on the test, you can, and so that you know exactly what will be on that, what will be on that, because then I'll have both those files in the test on Canvas, but it's, as you guys saw last time, it was kind of hard to see everything on Zoom, so I don't, there's not going to be a way for me to post that and the test together on Zoom. It'll be there up on Canvas that you can go and reference it, but yeah, I will put that up there. Other questions? I have a question. Wait a minute. Whoops. I moved it and I lost it. Give me 1 second to scroll. Okay. I have a question of trade. When will we get infinity with some of them? Are you saying, Sandra, on this test? Oh, cosine of pi over 2. Yeah, Robert, you do already have a helpful trig information, but with the steps. So I'm going to put one up that doesn't have the steps. And that would be the one that I'll post in with the test. I'm trying to see if I understand your question, so, Sandra. Go ahead.
We learn trig with the unit circle. So when we look at cosine of pi over 2, we're used to seeing that because cosine's x, it's just 0. But when we plug it in for stuff like on the homework number 7 in particular, it comes out to be infinity.
Okay. Let me pull up the homework. Number 7 from the section. From which section? From
9.7.
Okay. So let me.
It was one of the. It was like the second to last step.
Yeah. Let me just find where I have it on my. Okay. So. Oh, it's because. Okay. It's So so the reason it's infinity is because you were okay with all the other steps on that one, right? Or no?
Yes, I ended up getting down to the limit of b as b approaches pi over 2 of negative natural log absolute value cosine b plus natural log absolute value cosine 0.
Okay. All right. So the cosine of 0 is 1, right? So
right.
And if I plug in the b, so basically I didn't show all the steps. So if I plug in the b, so I have minus ln the cosine of pi over 2 plus ln of cosine of 0 is 1, right?
Yep.
Okay. And the natural log of 1 is 0. So this part goes away. Does that make sense?
Yes.
Okay. So the cosine of pi over 2, you're right. It is what is on the unit circle. The cosine of pi over 2 is 0. So, but now we're trying to take the natural log of 0, right? So that's why it's turning into, so again, the natural log, right? As I approach 0 on the natural log, I'm going down to negative infinity. So really what I'm saying is I have minus infinity, and so that's how I got positive infinity there.
Okay, I think I saw something weird on the homework then. I'm trying to pull it up to double check, because I think you actually put like the natural log of infinity, because that's what I wrote in on my sheet for fixing the problem. Oh no, you just put natural log of cosine b equals infinity. Okay.
Yeah. So I didn't.
Yeah, I think I was a little confused.
Yeah, what I'm guessing you probably did was you saw the infinity and you thought when I plugged in I got that the cosine of b was infinity, but I didn't. I just did that whole chunk all at once.
All right, perfect. Thank you.
No problem. Am I sure it's not cosecant? Like, oh no, I think I know what you're talking about, Brian. But no, she was talking.
That was before she got her question out. I was
yeah.
just thinking it was one of the ones that could go to infinity.
Yeah.
With a C in it.
Yeah. All right. Other questions from people that are hanging around.
So, with that, on the same thing, because cosecant, same thing with like tangent, go off into infinity too, right?
Correct.
Tangent's an infinity negative.
Correct.
Okay.
Yep.
I think, is there some helpful sheet or something that can kind of compile all of that into one so we can kind of see where, because the unit circle isn't always going to help us with that.
So that would be, I mean, I can put this up. I have a sheet that has the graphs of each. That's where I think the graphs of each one is more important. So I have a sheet from my trig class that has the graphs of each of the trig functions, and so it shows the asymptotes on there. Because that's where you end up going to infinity or not infinity.
Like a trig parent function sheet. Okay.
Yeah.
That would be, I'll look that up too.
Right, thank you. But no problem. I'll put it up in the handouts on our class.